British naval aviation in World War II lived in the shadow of American carrier operations. Smaller carriers, fewer aircraft, less publicity. The equipment was there, Swordfish, Barracuda, Firefly, but the attention went elsewhere. To Pacific battles, American task forces, kamikaze attacks. One victim of this attention imbalance was the ferry Barracuda, a capable aircraft that performed important missions, yet remained obscure. When museums collected World War II aircraft after the war, American types dominated. Barracudas were scrapped. All of them. Not a single example survived for future study. In 2018, that changed. Engineers, surveying for an undersea power cable, found a Barracuda buried in the Solent. The only complete example of the type left in existence, preserved by a combination of gentle crash dynamics and protective clay burial. What followed was archaeology's contribution to aviation history. Not just recovering an artifact, but recovering knowledge. How the aircraft was built, which factories contributed which components, how wartime manufacturing actually worked, what innovations the designers implemented, what problems they solved. The Barracuda's story became visible again through corrosion patterns, manufacturing stamps, structural details. The archaeology gave voice to an aircraft that historical narratives had rendered mute, restored its place in the record, made its contributions visible. The story begins not with archaeologists, but with engineers. September 2018. The National Grid's IFA2 project interconnection, France-Angleterre 2, was preparing to lay a high-voltage DC cable corridor stretching 240 kilometers from Fareham, near Portsmouth, to Normandy, France. Part of a £2 billion program to secure sustainable energy through offshore interconnectors. Before a single meter of cable could be laid, the seabed had to be surveyed. Protocol demanded it. The Solent and English Channel had been a war zone. 80 years of naval activity. 2 world wars, countless shipwrecks, unexploded ordnance scattered across the seafloor. Engineers from James Fisher Marine Services deployed remotely operated vehicles equipped with magnetometers and multi-beam sonar to scan a 180-meter-wide corridor along the proposed cable route. David Luetchford, head of IFA2 for National Grid, monitored the survey results. Over the course of the project, we inspected over 1,000 targets of interest, he later explained, many of which were found to be unexploded ordnance, not unusual given the history of this location. Most targets showed the chaotic signatures of wartime debris, twisted metal, scattered fragments. The sonar couldn't identify specific objects, only their rough dimensions and density. But one contact, 500 meters offshore from what had been HMS Daedalus, the Royal Naval Air Station at Lee on Solent, registered differently. The magnetometer readings were strong. Something large, ferrous metal, buried deep. Engineers deployed the ROV for visual confirmation. The underwater vehicle descended through murky green water. Visibility fluctuated with the tides, sometimes 2 meters, sometimes less than 1. The seabed here consisted of dense clay and silt. Difficult terrain for excavation. The ROV's lights swept across the bottom. At first, nothing. Then, protruding from the clay, the unmistakable form of an aero engine. Corroded? Yes, but recognizable. The distinctive shape of a Rolls-Royce Merlin. 12 cylinders, liquid-cooled, and behind it, barely visible through the silt, something that looked like a tubular framework. News of the discovery reached Wessex Archaeology, the heritage management firm retained for the IFA2 project. Marine archaeologist Ewan McNeill assembled the initial assessment. His team reviewed archival records, cross-referenced known aircraft losses in the Solent, consulted with the Fleet Air Arm Museum. The evidence pointed to a specific aircraft, Barracuda Mark II, serial number BV739, part of 810 Naval Air Squadron, lost on September 29, 1943. The pilot, Canadian Sub-Lieutenant Douglas Williams, had survived. Engine failure on takeoff. He ditched the aircraft in shallow water just offshore and swam to safety. But what made this discovery extraordinary was the preservation. Historical records indicated 2 Barracudas had crashed near Lee on Solent within 4 months of each other. Both due to engine failures on takeoff, both pilots survived. But this one BV739 had gone down in a controlled ditching, not a catastrophic crash. Dave Morris, curator at the National Museum of the Royal Navy, had spent 40 years collecting Barracuda fragments. His museum held the largest collection of ferry aircraft in the world. But the one missing from the set was the Barracuda itself. None existed. Anywhere. Since 1971, Morris had been assembling pieces from various crash sites, trying to reconstruct a complete aircraft. We have crash site remains from a number of Barracudas which have been recovered over more than 40 years of collecting, Morris explained. But they've all been subject to very fast collisions to high ground mountainsides. This is the first time we've come across a Barracuda which is largely still intact and in most of its original shape. The challenge had always been the fragmentary nature of the wreckage. Barracudas that crashed on land hit at high speed. The tubular aluminum framework crumpled. The skin tore away. What survived was mangled beyond recognition. Useful for studying construction techniques, perhaps, but inadequate for a full reconstruction. The Ferry Barracuda represented a revolution in British naval aviation. Designed in the late 1930s to replace the Ferry Swordfish biplane, the Barracuda was Britain's first all-metal carrier-borne torpedo bomber. A sleek monoplane with retractable landing gear, a crew of 3 seated in tandem beneath a continuous glazed canopy, and distinctive Ferry Youngman flaps that served double duty as dive brakes. The original specification S-24/37 called for an aircraft that could carry a 1,600-pound torpedo, achieve high speed, and operate from aircraft carriers. Ferry Aviation's design featured a shoulder-mounted wing, hydraulically retractable main landing gear that folded into recesses in the fuselage and wing, and an innovative high-mounted tailplane that improved stability. Development had been protracted. The intended power plant, the Rolls-Royce XE, was canceled. Engineers substituted the less powerful Merlin engine. The prototype flew on December 7, 1940. Early testing revealed underpowered performance. The definitive Barracuda Mark II received a more powerful Merlin 32 engine, generating 1640 horsepower. Production was distributed across multiple manufacturers. Ferry Aviation built the initial batches, but wartime demand required additional capacity. Blackburn Aircraft, Boulton Paul, and Westland Aircraft all produced Barracudas under license. Each manufacturer left distinctive inspection stamps and part numbers on components. These markings would later prove crucial for identifying which factory built which sections of the Solon aircraft. By mid-1943, Barracudas were entering service with 24 frontline Fleet Air Arms squadrons. 810 Squadron, based at Lyon-Solent, flew Barracuda Mark IIs in anti-submarine and training roles. The aircraft were new. Crews were still learning their capabilities and limitations. September 29, 1943, a routine training flight. Sub-Lieutenant Douglas Williams, a 22-year-old Canadian pilot, conducted pre-flight checks on Barracuda B V739. The aircraft had been delivered to 15 Maintenance Unit on July 17th, assigned to 822 Squadron at Lyon-Solent. Standard operations. Williams taxied to the runway, opened the throttle. The Merlin 32 roared. The aircraft accelerated, lifted off, and then power loss. The engine quit. Williams had seconds to react. Too low to bail out, not enough altitude to turn back. He ditched the aircraft straight ahead into the Solent. The Barracuda hit the water at flying speed. The impact ripped away the engine cowling. Water rushed into the cockpit, but the fuselage remained intact. The wings stayed attached. Williams escaped the sinking aircraft and swam to shore. The Barracuda settled to the bottom in shallow water, 15 meters deep. The dense clay and silt closed over it. The official record listed BV739 as Cat Z, Category Z, meaning total write-off. The location was noted, 500 meters offshore, but wartime priorities precluded recovery. Britain was fighting for survival. Aircraft were being lost daily. One more crashed Barracuda didn't warrant salvage operations, especially not in shallow coastal waters, where recovery would be difficult and expensive. The aircraft was left where it fell. Over the following months and years, silt accumulated. The wreck sank deeper into the clay. By 1945, it had disappeared entirely. No surface trace remained. Fishermen's nets occasionally snagged on something solid beneath the mud, but nobody investigated. The wreck became forgotten. Just another wartime loss in waters where hundreds of aircraft and ships had gone down. 75 years later, the archival research began. Wessex archaeology cross-referenced Admiralty records, squadron diaries, pilot debriefings. The evidence confirmed the identity. BV739, built by Boulton Paul, delivered July 17, 1943, lost September 29. Pilot survived. But the records also revealed something else. This Barracuda had gone down intact. Not a high-speed crash. A controlled ditching, which meant the airframe might still be largely complete. Previous Barracuda wrecks had been catastrophic losses, aircraft that flew into mountains, crashed on takeoff, exploded in flight. Those wrecks yielded only fragments. This one might be different. The initial ROV survey had confirmed the presence of an aircraft. Now, Wessex Archaeology needed detailed imaging. Engineers deployed high-resolution multi-beam sonar. The technology uses multiple sonar beams transmitted simultaneously to create three-dimensional maps of the seabed with centimeter-level precision. The results were astonishing. The sonar revealed not just the Rolls-Royce Merlin engine, but wings, fuselage sections, tail assembly. The aircraft lay partially buried, oriented roughly northeast-southwest. The nose had impacted first, driving the engine deep into the clay, but the midsection and rear fuselage appeared remarkably intact. The wings were still attached. One wing protruded from the clay at a slight angle. The other was buried deeper. Ben Saunders, senior archaeologist at Wessex Archaeology, examined the scans. The aircraft is buried in a silt clay mixture, which is not easy when it comes to excavation, he explained. Above the seabed, very little remains. But as we excavate down, more and more is becoming exposed to us. The recovery operation would be complex. The Ministry of Defense issued an excavation license. Wessex Archaeology developed the archaeological methodology. James Fisher Marine Services provided dive support, equipment, and surface logistics. The Fleet Air Arm Museum would receive the recovered components for conservation and study. Several factors complicated the operation. First, the depth. 15 meters was shallow for commercial diving, but the tidal currents in the Solent were strong. Divers would have limited bottom time. Second, the visibility. The clay and silt created near-zero visibility when disturbed. Divers would be working almost blind. Third, the preservation state. After 76 years underwater, the aluminum airframe would be fragile. Corrosion weakened the structure. The clay supported the weight, but lifting sections might cause them to collapse. William Gibbs, chief engineer on the Barracuda reconstruction project, studied the sonar imagery. He'd been working on the reconstruction for 5 years. The project aimed to create a complete museum-quality Barracuda using only original parts salvaged from crash sites. If you were to look at basically the plan form of a Barracuda and think, okay, let's build one of those, I think you would stop on day one, Gibbs admitted. It would just become too mind-boggling. The challenge was the sheer complexity. A Barracuda contained thousands of individual parts: tubular framework, stringers, formers, skin panels, control surfaces, the engine, landing gear, instruments, wiring, hydraulic systems. Most crashed aircraft yielded only a few dozen usable components. Gibbs needed hundreds. The Solent wreck represented a quantum leap forward. If even 10% of the aircraft could be recovered intact, it would be the largest single contribution to the reconstruction project in 4 decades. June 2019, fair weather finally arrived. The recovery operation commenced. James Fisher Marine Services positioned a dive barge over the wreck site. A crane was mounted on the barge deck. Archaeologists and divers assembled their equipment. Underwater positioning systems using USBL ultra-short baseline acoustic tracking allowed precise navigation despite zero visibility. Each diver carried a nanotransponder. When artifacts were discovered, the transponder could be placed directly on top, creating precise waypoints logged in the positioning software. This information could then be analyzed offline, creating a complete map of the excavation. The first challenge was removing the overburden. 2 to 3 meters of clay and silt covered most of the wreck. Conventional excavation techniques, digging with trowels and brushes, were impractical. The volume was too great. The visibility too poor. The current too strong. Engineers deployed an airlift dredge system. Similar to a giant underwater vacuum cleaner, compressed air injected at the bottom of a pipe created suction that pulled sediment up and away from the wreck site. The dredged material was pumped to the surface, where it passed through sieves. Any artifacts, hardware, or small components could be recovered before the sediment was discharged. Divers guided the dredge intake carefully, working by feel as much as sight. The clay was tightly packed. It had to be loosened before the dredge could remove it. But loosening too much clay at once created turbidity that reduced visibility to absolute zero. The divers worked in rotations, 20-minute bottom times, surface intervals for decompression, then back down. As the clay cleared, the Merlin engine emerged. The 12-cylinder V configuration was unmistakable. Coolant pipes still connected to the block. The carburetor, though corroded, was intact. Oil lines snaked through the engine bay. And on the engine mount, still visible despite corrosion, the manufacturer's data plate. The divers photographed everything. High-definition video captured the engine from multiple angles. Measurements were taken. Then came the question, could the engine be lifted as a single unit? The answer was no. The engine weighed approximately 750 kilograms dry. Filled with 76 years of accumulated silt and clay, it weighed well over a ton. More critically, the engine mounts had corroded. Attempting to lift the entire assembly risked catastrophic structural failure. The engine would have to be disassembled underwater. Components lifted separately. Before any component was moved, it had to be recorded. Archaeologists employed photogrammetry, a technique where multiple overlapping photographs are processed by software to create accurate three-dimensional models. Each major component received photogrammetric documentation: engine, wings, fuselage sections, control surfaces. The models served dual purposes. First, they created a permanent digital record of the wreck as found. Second, they provided detailed measurements that would guide the reconstruction project. The photogrammetry captured structural details invisible to the naked eye: rivet patterns, weld lines, assembly sequences. Helmet-mounted cameras recorded video continuously. The footage would be analyzed later, frame by frame, to extract additional information. Every moment of the excavation was documented. Nothing was moved without first being photographed, measured, and logged. As excavation progressed aft from the engine, the divers reached the cockpit section. The continuous glazed canopy had shattered on impact, but the framework remained, and inside remarkably preserved personal items. A pilot's boot, leather, waterlogged, but intact. Sub-Lieutenant Williams must have kicked it off as he escaped the sinking aircraft. The boot's preservation was extraordinary. Leather typically degrades rapidly underwater, but the anoxic conditions in the dense clay had prevented bacterial decay. The boot emerged looking almost new, a boost gauge, still attached to the instrument panel. The dial face was legible. Radium-based luminous paint had been used to make the markings visible in darkness. After 76 years, the radium was still faintly radioactive. Not dangerous, but detectable. Safety protocols required the gauge to be placed in a shielded container. Then came a find that astonished everyone: the underwing pitot head and mounting bracket, a delicate instrument that measured airspeed by comparing dynamic air pressure to static pressure. These devices were fragile, mounted on a slender tube extending forward from the wing. Aircraft recovery experts had never expected one to survive. Yet here it was, intact. The pitot tube unbroken, the mounting bracket still bolted to its original wing position. Ben Saunders handled it carefully. The fact that this was found intact implies that the Barracuda was almost at stall speed when it hit the water, he noted. A high-speed impact would have ripped the pitot head clean off. Its survival confirmed the controlled nature of the ditching. As the wings emerged from the clay, archaeologists documented construction methods unknown from any surviving blueprints. The Barracuda's wings featured a complex internal structure. Main spars ran spanwise, providing primary strength. Ribs gave the wing its aerodynamic shape. Stringers connected the ribs, supporting the aluminum skin panels. But the details were fascinating. Inspection stamps revealed which manufacturer built which components. Fairey Aviation stamps, Boulton Paul stamps, even some Westland markings. The Barracuda had been assembled from parts produced at multiple factories. Quality control stamps showed where subassemblies had been inspected and approved before final installation. On one front spar frame, a Fairey inspection stamp included the drawing number and part number. On another component, a Boulton Paul inspection stamp with issue 1 notation indicated it was from the first production batch. These markings allowed engineers to trace the aircraft's construction history with unprecedented precision. The distinctive Fairey-Youngman flaps represented cutting-edge aeronautical engineering for 1943. These weren't simple hinged flaps. They were complex mechanisms that could deploy to multiple positions: 20 degrees for increased lift during takeoff and landing, 30 degrees as dive brakes during torpedo and bomb attacks. The flap mechanism had been partially destroyed by corrosion, but enough remained to show the hydraulic actuators, linkages, and support structure. Photographs captured the details. Measurements documented the geometry. This information would be invaluable for the reconstruction project. No complete Fairey-Youngman flap system had survived anywhere else. Marine archaeologists studying the wreck began to understand why Sub-Lieutenant Williams survived. The Barracuda's structure had performed exactly as designed during the water impact. The fuselage absorbed energy through controlled deformation. The wings remained attached, providing flotation for critical seconds. The cockpit canopy framework protected the crew compartment from immediate flooding. Williams had ditched at minimum controllable airspeed, probably 90 to 100 miles per hour. The aircraft's nose hit first, driving the engine deep into the water and seabed, but the tail remained elevated. Water rushed into the forward fuselage, but the aft section stayed above the surface long enough for Williams to escape. The aircraft then settled slowly to the bottom. The wings oriented horizontally. The tail settled last. The dense clay provided a soft landing. No secondary impacts. No tumbling. The wreck came to rest in a stable position and was gradually buried by silt. 3 weeks into the excavation, the archaeological team faced a critical decision. Could the Barracuda be lifted intact, or would it have to be disassembled underwater? The ideal scenario was obvious. Lift the entire aircraft in one piece, transport it to the museum for conservation and study. But engineering reality intervened. The airframe was far more fragile than hoped. 76 years of corrosion had weakened the aluminum. The tubular framework had lost structural integrity. The skin panels were paper thin. More critically, the clay and silt had infiltrated every hollow space. The fuselage tubes were packed solid. The weight was enormous. Attempting to sling the entire airframe and lift it would almost certainly cause catastrophic failure. The fuselage would break in half, the wings would separate, decades of careful excavation would be destroyed in seconds. The decision was made. The Barracuda would be disassembled underwater, carefully, methodically. Each major section would be separated, documented, and lifted individually. Not the outcome anyone wanted, but the only realistic option. Dave Morris accepted the news philosophically. We're going to have to dismantle the aircraft underwater because unfortunately it is too fragile to bring up in one piece, he acknowledged. Despite the setback, the divers have managed to isolate a large part of one of the wings and are carefully preparing it for lifting. The new plan divided the aircraft into manageable sections. The engine would be disassembled into major components. Each wing would be separated from the fuselage at the wing root. The fuselage would be cut into forward, center, and aft sections. The tail assembly would be removed as a unit if possible. Every cut would be photographed and documented before being made. Separating the wings required cutting through aluminum structure without causing damage to adjacent components. Divers used hydraulic shears designed for underwater demolition work. The shears could cut through aluminum tubing and skin panels with controlled force. Each cut was planned in advance. Archaeologists marked exactly where the cuts would be made. Photographs documented the structure before and after. The starboard wing came free first. Divers attached lifting slings at carefully calculated balance points. The wing had to be lifted horizontally to prevent bending stresses. The crane operator worked slowly. Tension increased gradually on the lifting cables. The wing began to rise. Breaking the surface after 76 years, the Barracuda's wing section emerged into daylight. Water streamed from the rivet holes and panel joints. The aluminum skin showed heavy corrosion, staining green and white oxidation products. But the basic structure was intact. The main spar, the ribs, even some of the skin panels. Deck crew rushed to support the wing as it was lowered onto padded supports. Once out of the water, the team needed to work quickly, Ben Saunders explained. It starts to decay as soon as it comes out. She's been in the sea for 75 years or so. Conservation principles for underwater archaeological artifacts are straightforward. Keep the environment stable. Aluminum that has equilibrated with seawater over decades will begin aggressive aerobic corrosion if exposed to oxygen. The oxidation rate accelerates dramatically. Components can literally fall apart within days if not properly treated. The solution was wrapping. Conservators wrapped the wing section in water-saturated cloth, then plastic sheeting to maintain humidity. The goal was to keep the metal wet and cool, preventing oxygen exposure while slowing corrosion until proper conservation treatment could begin. When you're trying to conserve archaeological material, you want to try and keep it in the same conditions as to how it's been. Saunders noted, "What we're going to do is wrap it up and then keep it at least wet or damp to try and stop the corrosion continuing." Within hours of surfacing, the wing section was loaded onto a flatbed trailer. Destination, the Fleet Air Arm Museum at Yeovilton, Somerset. 160 kilometers northeast. The journey had to be completed quickly. Minimize exposure time. Get the components into controlled conservation as soon as possible. Dave Morris watched the trailer depart. He was absolutely amazed. To see obviously a piece of the Barracuda coming up after 76 years, yeah, you can still tap on the aluminum. I expected it to be a lot more corroded considering it's been down there for so many years. Over the following 2 weeks, additional sections surfaced. The port wing, fuselage sections, tail assembly components, hundreds of smaller parts, instruments, hardware. even fragments of wiring and hydraulic lines. Everything was cataloged, photographed, wrapped, and transported to Yeovilton. The museum's conservation facilities had never handled a project of this scale. Typically, they worked with small artifacts, instruments, personal items, fabric samples. Now they faced aircraft components weighing hundreds of kilograms, saturated with seawater, corroding actively. The first priority was stabilization, preventing further deterioration. The second priority was desalination. Removing salt from the aluminum would slow corrosion dramatically. The third priority was structural consolidation, reinforcing weakened components so they could be handled safely. Large fiberglass tanks were set up, filled with fresh water mixed with citric acid. This is just ordinary fresh water, tap water, mixed with citric acid, explained the conservation technician. The citric acid helps reduce the alkalinity of the seawater, producing a more neutral pH solution. This helps to stabilize the parts and reduce any further degradation. Components were submerged in the tanks. The citric acid solution began leaching out the salt, but the process was slow. Aluminum that had been saturated with seawater for 76 years couldn't be rushed. The desalination would take months. Water samples were tested weekly to monitor salt concentrations. When the pH stabilized and salt levels dropped to acceptable ranges, components could move to the next stage. As parts underwent conservation, William Gibbs began the painstaking process of identification. Every component had to be cataloged, matched to technical drawings if possible, assigned to its proper location in the aircraft structure. The inspection stamps proved invaluable. Fairey Aviation used distinctive ink stamps. Bolt and Paul used embossed metal tags. Blackburn Aircraft had their own marking system. By examining these stamps under magnification, Gibbs could determine which factory built each component. And often, from the drawing numbers, he could identify exactly where in the aircraft it belonged. The challenge was the absence of complete blueprints. Fairey Aviation's archives had been incomplete when the company ceased aircraft production. Many Barracuda drawings were lost, destroyed, or simply never preserved. The Fleet Air Arm Museum possessed some documentation, but it was fragmentary. Now, the Solent wreck was providing direct physical evidence. Measurements taken from recovered components allowed engineers to reverse engineer the original design. Three-dimensional scanning created digital models of complex assemblies. These models could be studied, measured, and used to fabricate missing parts for the reconstruction. The Solent Barracuda wasn't the only source. The museum had components from 4 other crashed Barracudas: DR-306, PM-870, LS-931, MD-956. Each wreck contributed different components. Together, they would provide enough parts for a complete reconstruction. But the Solent aircraft BV-739 was different. It was the most complete, the structure least damaged. Where other wrecks provided fragments, this one provided entire assemblies. And because it crashed at low speed, the forensic evidence was clearer. Archaeologists and aviation experts analyzed the physical evidence to reconstruct the crash sequence. The engine had separated from its mounts on impact. That was expected. But the manner of separation revealed details about the impact, angle, and speed. The propeller showed no rotational damage. The blades were bent, yes, but the bending pattern indicated the engine had quit before impact. The propeller wasn't windmilling, it had stopped. This confirmed engine failure, not pilot error or fuel exhaustion. The wing attachment points showed symmetric stress patterns. Both wings had remained attached through impact and the initial sinking. They only separated later, when the airframe settled into the clay. This indicated a level, controlled ditching. If the aircraft had rolled or yawed significantly, the stress patterns would have been asymmetric. The recovered instruments told their own story. The boost gauge showed low pressure, consistent with engine failure. The altimeter was frozen at approximately 200 feet, the last altitude registered before impact. The airspeed indicator had jammed at 105 miles per hour, just above stall speed for a Barracuda at ditching weight. Sub-Lieutenant Williams had done everything right. When the engine quit, he didn't try to turn back. Turning at low altitude with no power would have stalled the aircraft. The crash would have been catastrophic. Instead, he maintained flying speed, established a glide, aimed for the water, executed a textbook forced landing. The aircraft hit at minimum safe speed, nose slightly down to maintain airspeed, wings level. The impact forces, though substantial, were within survivable limits. Williams had seconds to escape before the cockpit flooded. He made it. The Barracuda did not. Metallurgists examined samples from the recovered aluminum. The alloys used in World War II aircraft were different from modern aerospace aluminum. They contained higher percentages of copper and zinc. These elements provided strength but reduced corrosion resistance. Under microscopic examination, the aluminum showed extensive intergranular corrosion. Corrosion had penetrated along the grain boundaries of the metal. This type of deterioration was insidious. The surface might look acceptable, but the internal structure was compromised. Strength was reduced by 50% or more. This explained why the aircraft couldn't be lifted intact. The aluminum had lost too much structural integrity. But it also explained the remarkable preservation. The corrosion had been relatively uniform, not the catastrophic pitting and cracking seen in aluminum exposed to alternating wet-dry cycles. The constant immersion in clay had actually protected the metal from worse degradation. Several recovered instruments used radium-based luminous paint, standard practice in the 1940s. Radium-226 mixed with zinc sulfide phosphor created glow-in-the-dark markings for night flying. The practice was discontinued in the 1960s when the health hazards became understood. After 76 years, the radium was still radioactive. Radium-226 has a half-life of 1,600 years. Barely any decay had occurred. The activity levels weren't dangerous, similar to background radiation, but conservation protocols required these components to be handled carefully. Stored in shielded containers, exposure time minimized. Some instruments would need specialized treatment. The radium paint would have to be removed before the instruments could be displayed publicly. A delicate process. The paint couldn't simply be scraped off that would create radioactive dust. Chemical solvents would be used to dissolve the paint, which could then be safely disposed of according to radioactive waste regulations. Remarkably, some hydraulic lines still contain traces of the original fluid. 76-year-old hydraulic oil. Chemically degraded? Yes, but analyzable. The museum sent samples to a petroleum engineering laboratory. The analysis revealed the oil was a mineral-based hydraulic fluid, typical of World War II aviation use, heavily contaminated with water, metal particles, and degradation products. But the base chemistry was identifiable. This information helped confirm the aircraft's service history. The hydraulic system had been serviced using standard Royal Navy specifications. The electrical system was largely destroyed. Corrosion had consumed most of the wiring, but junction boxes, switches, and some instrument connections survived, enough to trace the basic electrical architecture. One extraordinary discovery was a pair of batteries, still installed in their compartment, standard 12-volt lead-acid batteries, dated June 1943. "We couldn't resist putting a tester on the batteries," Dave Morris recalled, "and one of them still has 0.8 to 6 volts of current in it. It's absolutely remarkable that after 76 years on the seabed, the batteries were never intended to survive underwater. Lead-acid batteries short-circuit when flooded. The fact that one still held a measurable voltage after 76 years in seawater defied expectations. The explanation was probably the dense clay. It had created an anoxic environment that prevented the normal electrochemical degradation." The Fleet Air Arm Museum's archives contained records of other Barracuda crashes, terrestrial crash sites, mountainside impacts, high-speed accidents. Comparing the Solent wreck to these other sites revealed the unique nature of the find. Terrestrial crashes produced wreckage patterns dominated by impact trauma. High-speed impacts created debris fields. Components were scattered over hundreds of meters. The aluminum was shredded, torn, crushed. Useful for identifying individual parts, perhaps, but hopeless for understanding overall structure. The Solent wreck was different. Low-speed water impact, gradual sinking, burial in protective clay. The structure remained articulated. Parts that should be connected were still connected. This provided context that terrestrial wrecks couldn't offer. It showed how components fit together, how systems integrated, how the aircraft functioned as a whole. William Gibbs stood in the museum's workshop, surrounded by Barracuda components in various states of restoration. The Solent wreck had transformed the reconstruction project. "This is an incredible find," he emphasized. "There are very few blueprints of the Barracuda available, so this wreckage will be studied to enable us to see how the plane segments fitted together and how we can use some of the parts we currently have." The workshop contained the beginnings of a Barracuda. The cockpit framework, partially assembled. Engine mounts fabricated from measurements. Wing spars laid out on supports. But progress had been agonizingly slow. 40 years of collecting had produced maybe 10% of a complete aircraft. Now, with the Solent components, that percentage would jump. maybe to 30%, maybe more. We started finding there were hundreds of really valuable fittings, tube ends, constructional details, components for the Barracuda that we could harvest, Gibbs explained. You can't even begin to measure how useful this is for the project. Archivists delved into 810 Naval Air Squadron's wartime history. The squadron had formed at HMS Daedalus in January 1942, flying Swordfish biplanes. In April 1943, they re-equipped with Barracudas. The transition to the new aircraft type coincided with a training phase at Lee on Solent. Sub-Lieutenant Douglas Williams was one of dozens of pilots learning to operate the Barracuda. The aircraft was powerful but temperamental. The Merlin engine was reliable in most applications, but the Barracuda's installation created cooling and carburetor icing issues. Engine failures on takeoff weren't uncommon. Squadron records showed that BV-739 had only been in service for 2 months before the crash. The aircraft had accumulated maybe 50 flying hours. It was practically new. Whatever caused the engine failure, it wasn't wear or fatigue. More likely a manufacturing defect or a maintenance error. Researching Sub-Lieutenant Douglas Williams proved challenging. Canadian military records from World War II were extensive but not always digitized. Wessex archaeology made efforts to trace Williams and his family. In 2019, they were still searching. What was known came from squadron records and loss reports. Williams survived the ditching. He was uninjured. After brief evaluation, he returned to flight status. 810 Squadron continued its training cycle. In October 1943, they deployed to the Mediterranean theater. Williams remained with the squadron through the combat deployments. He flew anti-submarine patrols, shipping strikes, support missions. He survived the war. After demobilization, his trail went cold. The museum hoped that publicity surrounding the Barracuda recovery might bring his family forward. Relatives might have photographs, letters, personal recollections that could add human dimension to the archaeological evidence. While BV-739 lay buried in the Solent, other Barracudas made history. The aircraft's most famous engagement came on April 3, 1944. Operation Tungsten. The Fleet Air Arm's carrier-based attack on the German battleship Tirpitz in Kafjord, Norway. The Tirpitz was a strategic threat. The mere existence of the 42,000-ton battleship tied down Allied naval forces. Convoys to the Soviet Union couldn't sail without battleship escorts. British Home Fleet capital ships had to remain in northern waters, ready to counter Tirpitz if she sortied. In early 1944, British intelligence learned Tirpitz was nearly operational after months of repairs. Admiral Sir Bruce Fraser, Commander-in-Chief Home Fleet, ordered an attack. The weapon: Fairey Barracuda dive bombers. The target: the most heavily defended anchorage in Norway. From February 1944, Barracuda squadrons trained intensively. The training site was Loch Arabol in northern Scotland. The geography resembled Kafjord's steep hills surrounding a narrow fjord, perfect for realistic practice. Pilots flew from RNAS Hadston in the Orkney Islands. They practiced low-level approaches, dive-bombing attacks from 10,000 feet, escape routes through the mountains. Every aspect of the mission was rehearsed. Targets were marked on an island in the loch. Bombing runs were timed. Coordination between bomber waves and fighter escorts perfected. Lieutenant Commander Roy Sidney Baker Faulkner led the training. An experienced test pilot, he drove the squadrons hard. The Barracuda crews, many inexperienced, having never operated at sea, had to become proficient quickly. 85% of the aircrew embarked on HMS Victorias had never conducted carrier operations before. Early morning, April 3, 1944. British carriers approached within 120 miles of the Norwegian coast. HMS Victorious and HMS Furious launched the first wave: 21 Barracudas, 40 escort fighters, Hellcats, Corsairs, Wildcats. Swordfish aircraft conducted anti-submarine patrols. The bombers carried a mix of ordnance. 9 aircraft each carried a single 1,600-pound armor-piercing bomb. 22 carried 3 500-pound semi-armor-piercing bombs. 10 carried general-purpose bombs and anti-submarine bombs. The attack achieved complete surprise. German defenses were still manning their positions when the first Barracudas arrived over Kafjord at 5:29 a.m., exactly as tugs were preparing to assist Tirpitz out of her mooring for sea trials. The Barracudas attacked in a carefully choreographed sequence. First came the fighters, strafing Tirpitz and shore defenses, suppressing anti-aircraft fire. Then the bombers carrying high-explosive ordnance. Their bombs detonated among the flak positions, causing casualties and confusion. The main attack followed. Barracudas carrying armor-piercing bombs rolled into near-vertical dives. The ferry Youngman flaps deployed to 30 degrees, acting as dive brakes, slowing the aircraft to controllable speeds despite the steep dive angle. Pilots aimed for Tirpitz's armored deck. The bombs needed to hit from sufficient altitude to penetrate. Release was at approximately 2,000 feet. The bombs fell. 12 direct hits. Multiple near misses. Columns of water and smoke rose from the battleship. The attack lasted 14 minutes. The raid inflicted heavy damage. The armor-piercing bombs penetrated Tirpitz's upper decks. One bomb may have reached the lower deck before detonating. The explosions killed 122 German sailors, wounded 316 more. Anti-aircraft guns were destroyed. The radio aerials reduced to twisted wreckage. More important than the physical damage was the psychological impact. Tirpitz's crew morale plummeted. Repairs would take months. The battleship was out of action. British intelligence estimated 6 months minimum before she could threaten convoys again. British losses were minimal. 2 Barracudas shot down. 1 Hellcat damaged and ditched. 9 aircrew killed. A remarkably successful operation. Subsequent attacks, Operations Planet, Brawn, Tiger Claw, were planned, but cancelled due to weather. Eventually, in November 1944, RAF Lancaster bombers sank Tirpitz with tallboy earthquake bombs. The Barracuda served with distinction from 1943 to 1950, but it never captured the public imagination like the Swordfish biplane it replaced. The Swordfish sank the Bismarck, disabled the Italian fleet at Taranto, became legendary. The Barracuda, despite its technical superiority and combat effectiveness, was forgotten. Part of the reason was timing. The Barracuda entered service when the war had turned. By late 1943, Allied naval aviation was shifting from defensive to offensive operations. The focus moved to the Pacific. American carrier aircraft dominated. British contributions were overshadowed. Another factor was the lack of surviving aircraft. When enthusiasts and museums sought World War II aircraft to restore in the 1960s and 70s, no Barracudas remained. They'd all been scrapped. Without physical examples, public interest waned. The aircraft became a footnote, a specialist's topic, known to historians and aviation enthusiasts, but absent from the popular narrative. In 2020, Wessex Archaeology completed a groundbreaking project, a virtual reality reconstruction of the Barracuda wreck as it appeared on the seabed. Using photogrammetry data, three-dimensional scans, and high-definition video, archaeologists created an immersive VR experience. The reconstruction allowed viewers to dive to the wreck site, navigate around the aircraft, examine details up close. Information points provided context. When you approached the pilot's boot, text explained its significance. The radium-painted gauge glowed faintly, just as it had in the darkness 76 years before. Recreating the wreck of the ferry Barracuda in VR was a great way to bring the archaeology to life, the project archaeologist explained. It makes you feel like you are immersed underwater and gives the sense that you are discovering the wreck for yourself. The VR experience served an important educational purpose. Most people would never dive the Solent, would never see an underwater archaeological excavation. The technology brought the discovery to them. Schools used it for history lessons. Museums incorporated it into exhibits. Researchers employed it for analysis without needing to access the physical components. This represented a shift in archaeological practice. Traditional archaeology focused on excavation and analysis. Publishing results in academic journals, making objects available in museum collections. But VR offered something different: immediacy, accessibility, the ability to share the discovery experience with millions. By 2024, conservation work continued. The larger components, wing sections, fuselage frames, had undergone desalination and stabilization. They were structurally consolidated, weakened areas reinforced, corroded sections documented before removal. But the process was far from complete. Aluminum conservation is measured in years, not months. Each component requires individual treatment. Some parts need chemical cleaning, others need mechanical consolidation. A few require complete refabrication because corrosion has destroyed too much material. The conservation laboratory had become a learning center. Students from archaeology and conservation programs visited. They studied the techniques, participated in the work, The Barracuda project was training the next generation of maritime archaeologists and conservators. In the Fleet Air Arm Museum workshop, William Gibbs continued assembling the Barracuda. The project had evolved. Initially conceived as a static display, a museum artifact to be looked at, it now aimed for something more ambitious. A complete, structurally accurate reproduction. Not flyable, obviously, but authentic in every detail. The Solent components formed the core, original parts wherever possible. Where original parts were unavailable or too deteriorated, new parts were fabricated using traditional techniques. Aircraft-grade aluminum was sourced. Riveting was done by hand. Even the paint schemes were researched and reproduced. Progress was measured in small victories. A wing spar section fitted to its mounting points. An engine cowling panel shaped to match the original. The landing gear mechanism assembled and tested for operation. Each step documented, photographed, explained. As the reconstruction progressed, engineers rediscovered solutions to problems that had puzzled ferry aviation's designers in the late 1930s. The Barracuda faced contradictory requirements. It needed to be strong enough for carrier operations, light enough to fly from short decks, large enough to carry a 1,600-pound torpedo, maneuverable enough for dive bombing. The solutions were clever. The fuselage used oval section tubing, stronger than round tubing for a given weight. The wing structure employed Warren truss spars, triangulated framework that distributed loads efficiently. The Ferry Youngman flaps provided multiple functions, lift augmentation, dive brakes, speed control from a single mechanism. These innovations had been forgotten. Without complete Barracudas to study, the engineering knowledge was lost. Textbooks mentioned the aircraft, but they didn't explain how it worked. The Solent wreck was restoring that understanding. Metallurgical analysis of Solent components revealed the quality standards of wartime British aircraft production. The aluminum alloys were consistent with specifications. Thickness measurements showed proper material usage. Rivet installations demonstrated skilled workmanship. But there were also signs of wartime shortcuts. Some components showed evidence of being overstressed, repaired in service, modified in the field. The aircraft had been built quickly, under pressure, by a nation fighting for survival. Perfection was secondary to production volume. Interestingly, some of the field modifications improved the design. Strengthening brackets added where original structure proved inadequate. Reinforcing plates installed where cracks appeared. These modifications represented accumulated operational knowledge. Solutions discovered through use, not engineering analysis. The question arises, why invest so much effort to preserve and reconstruct one World War II aircraft? Museums contain thousands of artifacts. Resources are limited. Conservation is expensive. What makes the Barracuda special? Part of the answer is rarity. The Barracuda is extinct. No complete examples survived. This represents a gap in aviation history, a significant gap. The aircraft played important roles: attacking turpits, anti-submarine warfare, Pacific operations. Yet it exists only in photographs and written records. Archaeological recovery provides something photographs cannot: physical reality, the ability to touch, measure, study, to understand how components fit together, how systems integrated, how engineering theory translated to practical hardware. But there's a deeper significance. The Barracuda represents a moment in technological and social history. The transition from fabric-covered biplanes to all-metal monoplanes. The evolution of carrier aviation. The industrial mobilization of World War II Britain. The aircraft was built by multiple manufacturers: Fairey, Boulton Paul, Blackburn, Westland. Each company employed thousands of workers. Many were women, the Rosie the Riveters of British industry. These workers don't appear in official histories. Their names weren't recorded, but their work is visible in every rivet, every weld, every assembly stamp. Preserving the Barracuda honors their contribution, makes visible the labor that sustained the war effort. The aircraft is a memorial, not to battles or commanders, but to the skilled hands that built it. The Fleet Air Arm Museum developed educational programs around the Barracuda reconstruction. School groups visited the workshop. Students learned about archaeology, conservation, engineering, history. They saw conservators removing corrosion products, engineers fitting components, historians researching squadron records. The programs emphasized material culture, how physical objects reveal information written sources cannot. A rivet tells you about manufacturing processes. Corrosion patterns indicate environmental conditions. Wear marks show how components were used. This approach engaged students differently than textbooks. History became tangible. Not dates and facts, but things you could touch, problems to solve, questions to investigate. Several students who participated in the programs pursued careers in archaeology or conservation. The Barracuda Project inspired them. The Barracuda's combat history created connections with Norway. Operation Tungsten had been conducted over Norwegian territory. The Kafjord, where Tirpitz sheltered, is in northern Norway. Local communities remembered the attack. Norwegian museums reached out to the Fleet Air Arm Museum, offered to share documents, photographs, oral histories from civilians who witnessed the raid. Some Norwegians had been forced laborers, working on German defenses. They remembered the Barracudas diving through flak fire, the explosions, the smoke. This collaboration enriched the project. British archives documented the raid from the attacker's perspective. Norwegian sources provided the defender's viewpoint. Together, they created a more complete picture. The Barracuda wasn't just a weapon. It was part of a human story. People on both sides, some victims, some aggressors, all caught in circumstances beyond their control. During World War II, Britain and the United States developed carrier aircraft in parallel, but the approaches differed. American aircraft, Helldivers, Avengers, Dauntlesses, emphasized heavy ordnance loads. British aircraft, like the Barracuda, balanced payload with operational flexibility. The differences reflected strategic priorities. American carriers operated in the vast Pacific. Range and striking power dominated. British carriers operated in confined European waters. Versatility mattered more. The Barracuda could carry torpedoes, bombs, depth charges, mines. It could dive bomb, conduct level bombing, perform reconnaissance. One airframe, multiple roles. These distinctions were visible in the physical structure. American aircraft were heavier, stronger. British aircraft were lighter, more lightly built. The Barracuda's tubular construction saved weight but reduced durability, acceptable for European operations, problematic in the Pacific, where British carriers joined American fleets in 1945. Not all Solon components went to the Fleet Air Arm Museum. Some were distributed to other institutions, research museums, university collections. Each recipient agreed to proper conservation and public access. The goal was maximizing the discovery's educational impact. One engine component went to the Science Museum in London for their aerospace engineering collection. Several instruments went to the Imperial War Museum. Personal items, the pilot's boot, for example, were offered to the Canadian War Museum, given Sub-Lieutenant Williams's nationality. Structural samples went to metallurgy laboratories for ongoing research. This distribution ensured the discovery benefited multiple communities, not monopolized by a single institution. Archaeology should be public heritage, not private property. Making components available to researchers, educators, and public institutions honored that principle. All documentation from the excavation and conservation was digitized. Photographs, video, three-dimensional scans, conservation reports, assembled into a comprehensive digital archive. Stored on secure servers with multiple backups, this archive would outlast the physical artifacts. Aluminum inevitably corrodes. Even with the best conservation, components will deteriorate. But digital data can be preserved indefinitely, copied, migrated to new formats as technology evolves. Future researchers, decades or centuries from now, will be able to study the Barracuda through the digital archive. See the wreck as it appeared in 2019. Examine conservation procedures. Access measurements and analyses. The archaeology becomes permanent, even as the artifacts decay. Among the hundreds of components recovered, small artifacts sometimes revealed the most compelling stories. A manufacturer's tag with a possible date. A throttle linkage with Ferry Fulmar drawing references suggesting parts commonality between aircraft types. A brass hook and eye-band with stamped solder showing assembly techniques. One component puzzled everyone initially. Two flat, paddle-shaped objects. Wood, heavily waterlogged. Found in the cockpit area, archaeologists speculated. Butter paddles? Agricultural tools somehow mixed into the wreck? The answer came from American Barracuda enthusiasts. Those go into the air intakes, an expert explained, to stop sandy wind from blowing in and clogging up your engines. The Barracuda was going to fly in the Mediterranean theater. Desert operations. Sand was a threat. The intake covers prevented contamination during ground operations. Pilots removed them before flight. Finding them in the cockpit made sense. Williams removed them during pre-flight checks, placed them on the seat or floor. When he ditched, they were still there. A tiny detail. But it confirmed the aircraft's operational status. Ready for deployment. Prepared for desert conditions. interrupted by engine failure. Throughout the project, efforts continued to locate Sub-Lieutenant Douglas Williams or his descendants. Wessex Archaeology publicized the recovery. Canadian media covered the story. Veterans organizations shared information. Genealogy websites posted inquiries. The response was limited. Williams had survived the war. That was documented. But his post-war life remained obscure. Had he married? Had children? Where did he settle? The trail went cold. This wasn't unusual. Millions of World War II veterans returned to civilian life and vanished from historical record. They didn't write memoirs, weren't interviewed, just got on with living. Their service was an interlude, not the defining fact of their lives. But the hope persisted. Somewhere, Williams's relatives might exist. Grandchildren who never knew their grandfather survived ditching a barracuda in the Solent. The discovery could connect them to family history they never knew existed. In 2024, Wessex Archaeology published a comprehensive technical report, the recovery of a ferry barracuda from the Solent off the former RNAS Daedalus. The report documented every aspect of the project: survey methods, excavation techniques, conservation procedures, artifact analysis. The report appeared in an academic volume, Delivering the Deep: Maritime Archaeology for the 21st Century. It served multiple purposes, providing a permanent record of the work, contributing to maritime archaeological methodology, offering guidance for future aircraft recovery projects. One section examined the inspection stamps and markings. Though no Blackburn parts have been identified in the Solent Barracuda so far, the report noted there appears to be at least one example of a ferry ink stamp, though it is very faint and also appears to have been smudged, along with another blurred one on an electrical terminal block from the observer's cockpit. These details mattered. They allowed precise identification of production batches, manufacturing dates, quality control procedures, information invaluable for the reconstruction project. The Fleet Air Arm Museum began planning how to display the Barracuda once reconstruction was complete. Traditional museum exhibits placed aircraft on the floor. Viewers walked around them, looked up at the underside, inspected the cockpit through glass barriers. But the Barracuda deserved something different. The museum proposed a multi-level display, the aircraft suspended at viewing height, platforms allowing visitors to examine it from multiple angles, interpretive panels explaining its history, combat operations, the Solent crash, the archaeological recovery. Interactive elements would engage younger visitors. Touchscreen stations showing the underwater excavation, VR experiences simulating a dive to the wreck site, video interviews with divers, conservators, engineers. The goal was making the archaeology accessible, not just showing an artifact, but explaining how knowledge was created. The Barracuda recovery established new standards for underwater aircraft archaeology. Previous projects had recovered aircraft components, yes, but never with this level of documentation. This integration of conservation science, this public engagement. Several innovations became best practices. The use of USBL positioning systems for precise artifact mapping in zero visibility. The employment of photogrammetry before any component was moved. The immediate post-recovery conservation to prevent aerobic corrosion. The creation of VR experiences for public engagement. Other projects adopted these methods. Wreck excavations in the Pacific, Baltic Sea archaeological surveys, Mediterranean underwater heritage sites. The Barracuda project demonstrated what was possible. Raise expectations, advance the field. The project also highlighted threats to underwater heritage. The Barracuda survived because it was buried in stable clay, protected from scour, shielded from oxygen, insulated from temperature fluctuations. But climate change alters underwater environments. Sea level rise changes tidal flows, increased storm intensity causes seabed scour, warming water accelerates biological activity. Artifacts that survive 75 years might not survive 75 more. This creates urgency. Underwater heritage needs documentation now, before environmental changes destroy it. The Barracuda project showed how. But resources are limited. Thousands of aircraft wrecks exist worldwide. Millions of shipwrecks. They can't all be excavated. Digital documentation surveys, photogrammetry, environmental monitoring becomes crucial. As understanding of the Barracuda's design deepened, respect for ferry aviation's engineers grew. They solved problems that would challenge modern designers. Creating an all-metal carrier aircraft in 1940 required innovations in structures, aerodynamics, systems integration. The Fairey-Youngman flaps represented cutting-edge technology. multiple position slotted flaps with hydraulic actuation. The high-mounted tailplane improved stability without excessive weight. The folding wing mechanism allowed carrier stowage while maintaining structural strength. These weren't trivial achievements. Engineers worked with slide rules and hand calculations. No computer-aided design, no finite element analysis, no simulation software, just knowledge, experience, and painstaking hand calculation. The results, while not perfect, were remarkable. 7 years after the discovery, work continues. The Barracuda reconstruction has passed 50% completion. The fuselage framework stands in the workshop, wings attached at the roots, tail assembly positioned. The shape of the aircraft becomes recognizable. William Gibbs estimates another 5 to 7 years before completion. This is a 10-year project minimum, he acknowledges. Maybe 15. We're not rushing. Getting it right matters more than finishing quickly. Visitors to the museum can watch the work. The workshop has viewing windows. Interpretive displays explain what's being done, why it matters, how archaeology contributes to historical understanding. The Barracuda is teaching lessons, not just about aircraft design or World War II combat, but about how we recover and preserve the past. Douglas Williams survived his Barracuda ditching. He survived World War II. He lived a life beyond the few seconds when his aircraft hit the Solent water 76 years ago. That life remains largely unknown. Perhaps his family will come forward. Perhaps they won't. Either way, Williams's skill and courage on September 29, 1943, preserved the aircraft that is now teaching new generations. He executed a perfect forced landing under impossible conditions. Engine failure at low altitude, no time to maneuver, no second chances. Yet, he brought the aircraft down at minimum speed, wings level, saving both himself and, unknowingly, the most complete Barracuda that would survive to the 21st century. The Solent Barracuda project demonstrated archaeology's power to recover lost knowledge. Written records documented that Barracudas existed. Photographs showed what they looked like, but only physical examination revealed how they were built, how components integrated, how wartime manufacturing actually worked. The project also showed maritime archaeology's public value. Thousands followed the excavation. Millions viewed the VR reconstruction. Students learned archaeological methods. Engineers studied construction techniques. Veterans organizations connected the discovery to military history. The archaeology engaged communities far beyond academic specialists. Conservation will continue for decades. Aluminum conservation is never truly finished. The metal continues reacting with its environment. Corrosion, though slowed, never stops completely. Components require periodic retreatment, monitoring, assessment, intervention when necessary. This creates a commitment. Museums accepting archaeological artifacts accept responsibility for perpetual care. The Barracuda will need conservation attention for as long as it exists. Funding must be secured, expertise maintained, facilities preserved. Future generations inherit this obligation. The Barracuda's technological innovations influenced post-war naval aviation. The lessons learned from all-metal carrier aircraft design informed the jets that followed. Folding wing mechanisms, catapult attachments, carrier landing systems. The Barracuda wasn't the first to implement these features, but it contributed to their refinement. British carrier aviation in the 1950s and 60s built on Barracuda-era innovations. Aircraft like the Gannet and Sea Vixen incorporated solutions first tested on World War II aircraft. The institutional knowledge, the engineering experience, the operational lessons, all carried forward. Not every Barracuda crew survived like Douglas Williams. Operational losses were heavy. Training accidents killed pilots and aircrew. Combat operations cost lives. Operation Tungsten lost 9 airmen. Other raids, other missions, added to the toll. Each loss represented a family. Parents who received telegrams, wives who became widows, children who grew up without fathers. The aircraft preserved in museums and reconstructed in workshops exist because of their sacrifice. The Barracuda isn't just a technological artifact. It's a memorial. The project's greatest success may be educational. Students who visited the excavation, watched the conservation, studied the reconstruction. Some chose careers in archaeology, conservation, engineering. The Barracuda inspired them, showed them how past and present connect, how material evidence reveals stories. Museums exist partly for this purpose, not just preserving artifacts, but inspiring curiosity, encouraging learning, showing that history isn't dead facts, but living questions. The Barracuda project embodied this mission, made archaeology visible, accessible, relevant. The target completion date hovers around 2030 to 2032, but targets can shift. Conservation challenges emerge, funding fluctuates, technical problems require solutions. The timeline matters less than the quality. The Barracuda reconstruction will be complete when it accurately represents the original aircraft, not before. Upon completion, the aircraft will go on permanent display. Visitors from around the world will see it, the only complete Barracuda anywhere. A testament to engineering achievement, archaeological dedication, the determination to preserve what was nearly lost forever. The Barracuda project exists within broader efforts to preserve World War II aviation heritage. Aircraft are disappearing. The few surviving examples, mostly fighters and bombers, represent a tiny fraction of types actually built. Hundreds of aircraft models are extinct, known only from records. Underwater archaeology offers hope. Thousands of aircraft rest on the world's seabeds, some in shallow water, some accessible to current technology. Each represents a potential discovery, a chance to recover knowledge, preserve heritage. The Barracuda showed what's possible. Future projects will build on this foundation. 2,600 Barracudas were built. They served with distinction, attacked the Tirpitz, hunted submarines, supported Allied operations from the Atlantic to the Pacific. By the 1950s, all had vanished. Scrapped, crashed, forgotten. Until September 2018, when engineers discovered one buried in Solent clay, the last Barracuda, preserved by chance, recovered by dedication, now being reconstructed. A phoenix rising from the seabed. The aircraft represents more than itself. It embodies the work of thousands, designers, engineers, factory workers, aircrew. It connects us to a generation that built these machines under wartime pressure, that flew them into combat, that sacrificed when necessary. Preserving the Barracuda preserves their memory, their achievement, their sacrifice. Archaeology makes this possible, transforms mud and corrosion into knowledge and understanding. The last Barracuda teaches us about technology, about war, about the human capacity for both destruction and creation, about the importance of remembering. The story isn't finished. Work continues. But what began as an unexpected discovery has become something larger. A project that demonstrates archaeology's power to recover what was lost, to preserve what survives, to connect past and present, to teach future generations. The Barracuda flew for a decade, rested on the seabed for 75 years. Now returns to tell its story, the last of its kind, forgotten no more.